So is it live? Is it live? Hello, testing, 1, 2, 3. Okay, it is. Oops. Okay. All right. I'm starting to feel like making videos again, and I kind of want to just make a 5-minute video about the political situation and whatnot. I might do that after this. But also, I mean, what made me want to make videos is just, to share things that I'm thinking about, right? Also to get conversation on them, but it's possible to categorize those two things differently. And in a way, this medium has become, or maybe it always was, uh, aimed at disseminating information. So something I like, that whether you like it or not, I'm just going to tell you about it. If there's people that like it, then they would make this super popular. So on Facebook, I found this because I started using Facebook back when there was the Hawaiian eruption. And I found this. See, the thing is, it would be nicer if this was, you could actually see it. See, that's much better. If I do this, move it up here and fit it in. Top part could go, right? Anyway, on Facebook, an aesthetic graph function group. Now, I've always liked this. Like, I'm a big fan of this graph. It's a private group. To join it, they ask you to do it. So, but let's see, 1/x is nice, and then sine of x. I love that. That's a good one. So aesthetic graph function. Okay, so my really nice one was this guy. What? I think I made a real discovery here, like Mandelbrot's. I'm going to show a bunch of different ones. Most of them are just, interesting to me. This one is the sine. Oh, that's other people's. This one, no. Oh, here, 23 more. This one. I've generalized this and whatnot. Okay, that didn't work. Okay, so what you can do with this site Desmos is you can graph anything. So, for example, I just did that graph. No. Right, so it's really general. You can go y equals x. There's a straight line. Y equals x squared, or cubed, or fourth, fifth, or sixth, or seventh. You ever notice that, how they basically go back and forth, right? There's two kinds. There's the U-shaped one, and there's the inflection-shaped one. And when you go 5 or 9 they're all the inflection shape, but the thing there gets to be a little. So this thing is, you also, it's actually like yx equals um, x. You don't necessarily have to solve the equation. That's cool. This is, of course, nice. Love that sign. And then the cosine, which is the same thing, but just shifted a little bit. It's shifted, what is it, pi over 2? It's nice. Look, if I type pi, it makes a pi divided by 2. Oh, wait, no, that's not right. I mean, in here, minus pi over 2. Y equals sine x. See, just shifted by pi over 2. Cosine and sine are the same thing, just phase. That's a phase shift, it's called. So let's say I take the adjustment out. So the red is the cosine. It's just out phase by, what, 90 degrees. There's a lot of neat mathematical things that I really love. And I don't think I'm very good at mathematics, but there's some things about mathematics that I love. So one of them is complexity. I'm going to go down here and get this thing again. I don't need these. Those are, here, this thing. So if you look at it, oh yeah, I just remembered. If anybody shows up, I'll be able to see. Oh, hey, so somebody showed up. Phoenix. Does it show me somewhere how many people are watching? I think as far as regular people go, YouTube had, and I think still has, a tremendously positive potential between people sincerely interested in sincere conversation, but can't see the rest of the comment, or it's coming. Okay, so you can also do polar coordinates. So let's do a polar coordinate example. So r equals, 5. It's a circle with radius 5. Boom, see? You can, this thing is just lovely. You see, it's at 5. If r equals a theta, and like pi, if I type theta, it turns into theta, then of course it's a spiral. So that's the radius is whatever the angle is. Right, so I could tighten that up by putting a small number in front of it, let's say 0.1. And you notice with the polar, it goes from r, it goes from some range for theta, right? Because if I go 32 pi, then it's going to go out further. Now a neat thing here, look, I can go a pi, and it's going to say, hey, I need a equals 10. It'll go as far as I say. Let's say a equals 32 pi. Okay, and then, oh yeah, I can do it that way. Let's say a equals 90. It makes a slider. Right? So that's as the theta goes around, right, in polar, the theta goes around instead of x running, you get some sort of a radial plot. So if r equals sine theta, you just get a circle out of that. And as it goes around multiple times. Right, 2 pi is a circle. Okay, so this guy, I mean, I think I discovered something on the order of a fractal here. Look, so it's r equals sine of modulo. Now, modulo is a remainder function. It returns whatever's the remainder. So if you had modulo, 3, or if you had modulo 7 comma 3, it'd be like, well, there's a whole 3, and a whole 3, that's 6, and there's 1 left over. Mod would be the 1. So this involves using the modulo of the theta. So it's a sine of theta moduloed pi over some number that I put into a slider. Let me check the comments. Phoenix Chastain is here. But ... Some folks are more interested in monologuing than sincere back and forth. Well, I mean, I like both, but I'm definitely here for the conversation, which I think is faded. I mean, not to insult the people that watch my channel, because I think most, many, a big 60 to 90%, have the same attitude of wanting to converse, right? Not just consume opinions. Some older YouTubers just stopped replying to response videos because they became more self-promoting than topic promoting. But they're not as interesting as they think they are. So though they follow the self over topic trend, they hadn't factored in the fact that their self isn't that interesting because very few people are as interesting as their topics. Yeah, I agree. I'm making a video. Sure you can. Because look, I've got my my beautiful discovery on there. So this line right here is a glitch in the software. Okay, so this is from 0 to 32 pi. And it's got a very interesting, so it's that sign of the mod of the thing over my value, and then also pi to the 1 over my value for the arctangent. And again, you can look at both of these to see what their impact is. But what's interesting about this, why I think it's so great, is look at how different the graphs can be, right? So there's this type, that. There's that one. It's a 2. That's nice. 1.5. Right at 1, there's this sort of thing. All just with the changing of one variable. So that's, oops. You bumped the chair, Jen. So there's this, no, that's okay. It had a cool effect. There's this at 0.5. You can animate this. So that's all pretty fast. Let's see the slowest rate. So that was interesting. I want to go back and look at that. These ones are like that. So many different patterns from one equation and one free variable. Plus, they look symmetrical, but none of them are actually symmetrical. Like this one shows an example. It doesn't even look that symmetrical, but they're all sort of that way. And then I've tried other things because, see there, it's just going around and around every time, getting the same thing. It's a nice one. And again, see the thing about these that look symmetrical, they're not exactly. If you look, the dark part isn't exactly the same, though they're sort of the same effect. It's nice. So I'm just sliding the value of A in my equation. These little lines that show up like this one are artifacts of the graphing program. So that keeps going. All right. Hey, Black Heavyweight. Well, I don't know. The thing is about back and forth is you can have some sort of IM system. Yeah, it's back and forth with people you already know. What if you want to take part in the public conversation? So you put it up there, and whoever shows up, maybe some 20-year-old that just decided, hey, I could take part in this thing. That's interesting. And so it's the public conversation. So it's an IM, but it's public. And yet, you don't want to just randomly be hooked together with whomever. I think, searching videos by keywords, finding something you're interested in, and then watching the replies, the old YouTube thing was the best. Okay, so let's see what other functions I have. Here's what I've been working on lately is making something that can follow another function. So here's the function that it's following, this orange sine wave. And I have it swerving some circles, but let's say it's trying to do a circle, so those are zeros. Didn't expect this. That's a sine wave. This is a parametric wave following. See what's going on there. That should be going perpendicular. So this black line is a parametric curve that's following this is the rate of change. What am I missing? The black curve is right here. It's being, those 2 points are calculating it in terms of time. Oh, that's right. Yeah. Okay. Okay. Sounds good. So now it's going. It's doing a sine wave that's perpendicular to this sine wave, right? So that's there, that there. So for example, let's say I do this as equals 1. See how it just follows this wave, and it's always 1 away. Here, it's 1 away as it curves around, down around that thing. So this is it doing a sine wave, and if this was equal to, might see it more seen. So that's sine wave. And then this is a general purpose. What it does is it can take the, it can track that curve. So this is, let's make this bigger. This is the frequency of the orange wave. Not the only frequency. There's these two. Well, let's just make it a regular sine wave. And let's make the frequency really small. There you can see. So see, I have a sine wave. That's this sine wave down here. This one right here. See, it's a sine wave. I can make, so it's got a frequency, I can lower the frequency. Right, so it's a sine wave following another sine wave. And it's taking a derivative to get the slope. So I can change this to v squared, and then it's going to follow that. So it's a sine wave following that. And I will take away this part to show you. Let's see here. So I also have the general purpose of, wait, why are those not showing? Oh yeah, of this thing. So let's make this a broader 0.01, so it's broader. Okay, and so what I have is this x1 slider right here, and what that does is it changes the value of x. So if I move the value of x, I see. Let's make this one like this so I can zoom in because I have a range. Okay, so basically the green line here is a tangent to the curve, to the orange curve, and the blue is perpendicular at the point of x1, which is right here, so 48. So let's say I move that down to 40, so you can see how that remains perpendicular. And that's what, this is what I'm using. See, it only goes up to 16 pi because that's, you know, around 50. Now I could change this slider to be 32 pi, and it go further. See, so that hooks in, and that's because this is the tangent and the normal, and at that point, that's what I'm using to calculate the rest of these things. Black heavyweight. Well, I learned to do this stuff just from, I mean, I have a philosophy degree, but I paid a lot of attention to mathematics, and I really love mathematics. And so now that there's software tools like this, it becomes really straightforward. All right, so some other, these are all my following curve. Tangent. Here's one I did just where you can make a point on a circle. See, so this A changes a coefficient that puts that point around a circle. Just checking on that. So that's a parametric thing with cosine and sine. Parametric parabola. Here's this one's animating right now. So the function showing here is x1 is t, boom, boom, that becomes x and y. So this is a1 times sine b1 cosine p1v. So this creates the frequency, this p1, right? It's how fast the angle is cycling. p2 the same. b2, this is the amplitude of that cycling, and then I've wrapped both in a sine wave, and then I've given them an amplitude. So amplitude A1 and 2 you're going to see is the outside stretch. B2 is an inside stretch, which acts as a frequency on this subcosine. So you're going to see this as a sort of stretching the frequency of the inside lines, right? And so it still stretches the outside as well, though, because it's a percentage. And then this is the inner frequency, which is just going to do affect the fat pattern. So it's a bunch of these kind of patterns. So let's say I move this down to 0. I like the parametric curves. This was based on Fermat's spiral, and I definitely like this guy. Now I also have the negative. See, this is from negative 8 pi to 8 pi. I have the same thing with a negative r, which puts that at the bottom. This is also very rich with based on f. So f of 1. So this is r equals s of theta. S of theta is the arctangent of coefficient times sine of a frequency coefficient times theta plus a different coefficient times sine of a different coefficient times theta. So this is the frequency, right? And it plays with this other frequency when they line up. Like here's both of them at 4, right? When you go just off a little bit, it starts to make. And they're not spirographs, but it's the same kind of idea. And then here's the inner magnitude effect. It's not a magnitude effect. So I like that one. Let's see. Here's a simulated signature. I thought this was pretty cool with a. It looks like a doctor's signature, right? That's another parametric. These are various parametric equations with parameters animating. Let's see. I know there's a couple more. This is the beginning of that one. Here's one. This is regular scale. Like this guy. It's an interesting equation. Again, it's a parametric based off a sine wave on a sine wave. Let's see. I like this animation. It's another parametric thing. So it's playing with sine waves. But when you do it parametric, you don't have to see, when you have a regular formula, you have to follow along with x. When you do parametric, you follow along in t, so x can go back and forth too. So you can start with regular formula and then weird them out. Like this guy. This is, you can see right here, sine AT plus sine BT, where and y equals cosine CT. And I'm animating A1, where A gets defined as A1 times pi. This is not the same, but is related to that sine arctangent flower thing. So that's a formula with one of the coefficients animated, right? So that each one is a formula, so the x or the theta gets, or the parameter t gets exercised. But some coefficient is animating, right? So each frame is with a certain set of coefficients. And right here I have 3 coefficients animating. So here is a simple one. You've got this interesting equation, I think, up here. And just A is animating, so I'll stop A. So depending on A and B and C, you've got different look. And when I started, I was just animating A. I like this one a lot. So this is just it has 3 coefficients, a magnitude coefficients on the outside of sine waves, but they're inside other sine waves, and then one purely frequency, and then one plus d just is what creates this inner circle, right? So it's always bigger than that. And then if you change these, oh yeah, and n1 is the range of the plotting, right? See how there's n1 in there? So I'm just plotting more of the same thing when I do that. So I like to send that at 16 or 32, something like that. Now if I change D, see it's just that inner circle size. Let's say we set that at 5. So this is C1, this is the outer scalar. And so we're scaling there. This is one of the inner ones. So I love this shape. Pretty cool. No mod. Mod can kind of be cheating. So it can make all this. You can kind of see where its flexibility is. here they're just animating back and forth. All right, here's the original of that. It's a similar, this is a similar function with the original of that last one. Kind of just animates like this. What else? Untitled graph, what was that one? I don't know, that's pretty cool. So what I'm doing is I'm just moving the coefficients of an equation that I've created, this equation up here. And it's creating all of these different actual figures based on the coefficients. All right, I guess I'm done with that. I'll finish with this one. What's this one called? Hypnosis. So that's a formula. Yeah. Okay. That's enough of this. I might make another video though.